The purpose of this video is for us to learn how to use directed acyclic graphs to decide which variables we need to condition in our model in order to control for confounding in the association between our exposure and our outcome variables. And I'll start out by pointing out that we, in a shorthand way, call directed acyclic graphs DAGs. So this is pronounced DAGs, and so I'll be referring to DAGs during this video. Now let's think back to the example we were using in the previous video, which was called confounding and conditioning on a variable. And in that video, we were looking at whether coffee drinking was a cause of COPD. And we said that a tendency to use stimulants was causing both coffee and smoking, and in turn, smoking was causing COPD. And in the previous video, we conditioned on smoking, which we are going to indicate by putting a box around smoking. And we saw how conditioning on smoking removed the confounding bias between coffee drinking and COPD. But we didn't talk about, in general, how you use the DAG to decide which variables you need to condition in order to remove or at least minimize the confounding between your exposure variable and your outcome variable. So that's what we want to do here. So the outline of what we're going to do is we're going to start by first looking at the anatomy of a DAG, its parts and how it's constructed. And then we're going to go into the theory of how you use a DAG to decide on which variables you need to condition to control for confounding in the exposure to outcome association. Now, one of the things I want to say is that we're going to be, in the end, using some software that will actually help us to analyze our DAG and decide which variables on which we need to control. But I think even when using that software, it's important that you understand the underlying theory behind it so that you can use it appropriately. So we're going to start with the theory, and then we will move to the software tool that's going to help us to make the process much easier. Now, starting out, I want to point out one characteristic of DAGs, which is that they might have both measured and unmeasured variables inside of them. So for example, here, we might have data on coffee drinking and smoking and COPD on study participants, but it's quite likely that we wouldn't have any kind of measure of their tendency to use stimulants. So this would be probably, in most cases, an unmeasured variable, and these three would be measured variables. And that's okay. In fact, it's normal that we will have both measured and unmeasured variables in our DAG. So when talking about DAGs in general, sometimes I'm going to want to use letters to represent variables without actually naming the variables. So the nomenclature that I'm going to use is I'm going to use E to mean exposure variable. D is going to mean the disease or outcome variable. And for measured variables, I'm going to use the letter M. And if we have more than one, I would just label them M1, M2, M3, etc. And for unmeasured variables, I'm going to use the letter U. And again, if we have more than one, I'll just number them U1, U2, U3. So our previous example would be written, we would have an exposure variable, we would have an outcome variable, we have one measured variable, and we have one unmeasured variable. And the unmeasured variable is causing the exposure, the unmeasured variable is causing the measured variable, and the measured variable is causing the disease, and we are conditioning on the measured variable. Now, one of the first things I want to point out here is that these are called directed acyclic graphs. So what does the acyclic actually mean? So what the acyclic means is that you cannot get from any variable in the DAG back to itself by following a path of arrows. So, for example, this DAG that we've drawn over here is acyclic because if from U1, I cannot get back to U1. I have two paths I can follow here. One is going here through M1, but it gets blocked at this disease variable because both arrows are going in. I can't go this direction. And U1 going through exposure goes here. Again, it gets blocked at the disease variable. So this is acyclic. We couldn't, for example, have something like this, where we have some measured variable and it goes in a circle. This would be cyclics because we can go from M1 back to itself, we can go from exposure back to itself, etc. So this would be a cyclic graph, which is not allowed. So if you find yourself in a situation where you think that to encode your ideas about reality, you need a cyclic graph, you should just come and talk to me. There might be some ways that you can get around it, but they're sort of beyond the scope of this class. And I expect that probably all, or at least the vast majority of you, won't have that kind of need for a cyclic graph. Now, there are ways to deal statistically with cyclic graphs, but we're not going to be talking about that in this class. So let's define some terms that we will be using sometimes. And one way that we talk about the relationships between different variables in the DAG is to use a metaphor of family relationships. And so we use the terms parent, child, ancestor, and descendant. So you can probably guess what these terms mean already. A parent is a variable that causes another variable. So for example, exposure is a parent of disease, U1 is a parent of M1, etc. And a child is just the child of the parent. So M1 is a child of U1, disease is a child of exposure, and ancestor happens, well, a parent is a kind of ancestor, but you can have earlier generations. So for example, for the disease variable, M1 and U1 are both ancestors because they are upstream causally from the disease, and descendants likewise for U1, both M1 and disease are descendants of U1. So those are sometimes terms that we use when we're talking about the relationships between the variables in our DAG. Now, when we think about the different components of a DAG, we think of it as having three major parts. It has variables, it has arrows, and it has missing arrows. Now, it might seem strange to consider missing arrows as a component of the DAG, but the reason we think of it in this way is because a missing arrow is actually the most important component of the DAG. A missing arrow is a strong claim that there is no causal relationship between one variable and another variable. So one of the principles that you should remember is that if you're not certain whether there's a causal relationship between one variable and another variable, the conservative choice is to put the arrow there. So if we look at our previous example, the idea that the absence of an arrow means that there is a strong causal claim. It means that, for example, we are making the claim that among these variables, there is no causal effect of smoking on coffee. Smoking doesn't make you drink coffee. And likewise, we're making the claim that coffee does not make you smoke. Now, beyond this, one of the claims that we're making is that in terms of this tendency to use stimulants and its effects on COPD, we're making the claim that all of the effects of this variable on COPD are operating through two pathways. One pathway is through the pathway of smoking, and the other pathway is through the pathway of coffee. So, for example, we are saying that there are no other pathways between the tendency to use stimulants and COPD other than the effects on smoking and coffee. Now, if we're not sure about that, if we're think that, well, maybe there are other pathways, I just can't think of them, then what we actually need to do is we need to draw an additional arrow over here. And so now we have 3 pathways. We have one pathway through smoking, we have one pathway through coffee, and we have another pathway that we haven't named, but we're just saying that we think there's a possibility that there are still some effects of the tendency to use stimulants on COPD that don't operate through the pathways of increasing smoking or increasing coffee drinking. So this gets to a very important principle. And to see the principle, I first want to point out the 2 basic ways that you can expand a DAG. So let's use the example of smoking is a cause of COPD. And the first way that you can expand a DAG is to add variables in the causal chain. So for example, for smoking as a cause of COPD, I might say that what actually happens is that smoking causes tissue damage in the lungs, and it's that tissue damage that causes the COPD. So this way I'm adding one variable in the causal chain, which is tissue damage. Now another way that we can do it is to add extra causal paths between 2 variables. So for example, I might say that in addition to tissue damage, another thing that smoking is causing is an increase in the inflammation in the lungs. And it's actually also not only the tissue damage, but the inflammation that is causing the COPD. So now that we've seen the ways that you can expand a DAG, we can get at the very important principle. Whenever you see in your DAG that you have this kind of chain of causes going in a line, or you have multiple pathways between one variable and another variable, you need to ask yourself, is that a complete view of your idea of the causal structure of reality? For example, if we think that it is smoking leads both to inflammation and tissue damage, and those both lead to COPD, then this one in the middle here is wrong, because this says that all of the effect of smoking on COPD passes through tissue damage, that it's only the effect on tissue damage that is having an effect on COPD. We've left out inflammation here. So if we are not certain that everything is passing through, because remember, the absence of an arrow is a strong causal claim. What we should be doing here is we should be adding another arrow like this. We don't necessarily have to have a name on the arrow. What this means is that, okay, we think that at least some of the effect of smoking on COPD is happening through this tissue damage, but there may be other pathways. And we can have that down here as well. We may say, okay, well, we know that tissue damage and inflammation, or we hypothesize, are 2 ways that smoking is causing COPD, but there might be other pathways. If we have that idea, there might be other pathways, then we need to put an arrow here. Because remember, the principle is, if you're not certain, then you should put the arrow there. The absence of an arrow is a strong causal claim that there is no causal effect working through that pathway. Now that we've talked about the structure of a DAG and some of the principles about building a DAG, what I want to turn to now is how we use the DAG to think about which variables we want to condition on in order to control the confounding between the exposure and the outcome variable in our model. And to do that, I want to start with an idea, which is very important, which is going to expand our ideas about the different structures in our data that can account for an association that we see between exposure and disease, for a pattern in the data that we see between exposure and disease. And these are what we've already seen. We've gone over them many different times now. And what I want to do is I want to add a 4th one. Now, these 3 are the 3 basic causal structures that we can use to account for an association between exposure and disease when we're just looking at raw data, when we're just looking at the data as they exist in our data set. But now that we've introduced the idea of conditioning on a variable, what we need to do is we need to add a fourth one. And it looks like this. Essentially, if you have an exposure and you have a disease variable, and these two variables are parents of something else. And notice that this is just the opposite of what we saw over here. Here the arrows are pointing from something else into both exposure and disease. Here the arrows are going in the other direction. Now in this situation, if you condition on this other variable, which is the descendant of both exposure and disease, what you're going to do is you're actually going to induce an association between exposure and disease. If you don't condition, then the structure will not cause a pattern to occur between exposure and disease. But as soon as you condition on the variable, then you will have an association between exposure and disease within at least one level of the variable on which you're conditioning. But you probably don't have to worry about that little detail. Just think about this as, in a more simple way, that if you condition on a descendant of both exposure and disease, or any two variables for that matter, you're going to induce an association between those two variables. And here I've drawn it as conditioning on a child of exposure and disease. But in fact, it's even more general than this. If, for example, you had another variable here, and you conditioned on that variable, even this will induce an association between exposure and disease. So it really is conditioning on any variable which is a common descendant of both exposure and disease that will cause an association between those two variables. But one thing we should note here is that the farther away from the exposure and disease variable we get in this causal chain here, the weaker the association is going to be that we induce by conditioning on a variable that's a descendant of both exposure and disease. So if we condition on this variable down here, this other variable, we will see a pattern between exposure and disease, but that pattern will be weaker, most likely, than the pattern we would see if we conditioned on this variable here that's called something else. Okay, now to think about how we actually use the DAG to decide which variables on which we should condition to control confounding between exposure and disease. Let's look at our previous example. And the first step here is always going to be to identify the causal pathway between your exposure and your disease. And here you're following the directions of the arrows. Now here we have a very, very simple pathway. They can be more complex than this, but what we have is essentially we have a single arrow going from coffee to COPD. And so this is the causal pathway between coffee and COPD. Now, if we had other arrows here, for example, if we expanded this to have multiple variables in the middle, multiple paths, then we would be including all of those inside this causal pathway. Or if we had multiple steps like in a linked chain, we would include all of those variables that are in the pathway between coffee and COPD following the direction of the arrows. And one of the principles is that we never want to condition on any of those variables that are in the causal pathway between exposure and the outcome. Now, the next thing that we want to do after we've isolated all of those causal pathways, we don't want to touch those causal pathways, but now what we have to do is we have to look at what's remaining in the DAG. And what we're looking for is now we're for a moment, we're going to ignore the directions of the arrows, and we're going to find all of the pathways that don't go through this part that we've highlighted in green. We don't want to use these pathways that are from exposure to outcome anymore. We want to use all of the other pathways. And if we can find any pathways that go from the disease variable back to the exposure variable, we just want to note those pathways. And for this diagram, there's only one pathway. Basically, it goes back through smoking, and then it goes back to coffee. So what we have to do, this is called a backdoor path. This is a backdoor path from disease back to exposure. And essentially what we are going to do is we are going to identify all of the backdoor paths that exist in our DAG. And we're going to make sure that all of those paths are blocked. And the way we block those paths is by deciding on particular variables on which we're going to condition. Now, there's a possibility of blocking the entire path at any one of the variables along that path. You only need a single block on the path in order for the entire path to be blocked. And so what we need to consider is if there are existing any natural blocks in the path. If there are, then the path is already blocked. We don't have to condition anything at all. Or if there aren't any natural blocks in the path, then we have to decide on one of the variables that we are going to condition. Because if we condition on the variable, that is another way to block the path. Okay, so let's look at the general principles. Now, to talk about this, I'm going to be using one term, and I can't remember if I've introduced it already or not. But the term is, I'm going to be referring to the variables in the DAG as nodes in the DAG. So each of these is a node, and what we want to find out is if there is any single node which is blocked on this backdoor path. If it's blocked, then the whole path is blocked, and then actually we don't have to worry about confounding between exposure and outcome anymore. But if the path is open, we need to choose a variable to condition on in order to block this path. Now, one thing I should also note is that if we have to condition on a variable, obviously, we can only condition on variables that are measured, because in order to condition on a variable, you remember we split the problem into different parts within each level of the variable on which we're conditioning. When we were looking at coffee drinking as a cause of COPD in a previous video, we conditioned on smoking by doing the problem within smokers and within non-smokers. We conditioned on smoking, and we found that there were different odds ratios within those levels of smoking than when we just looked at the data naively, looking at the association between coffee drinking and COPD. Now, in that one, we had conditioned on smoking, and that actually blocked the backdoor path between COPD and coffee. And why did it do that? Well, we need to look at the principle more generally. And to look at that, what we can recognize here is that the pattern of arrows around the measured variable, in this case, looks like this. If we drew it sideways, it would look like this. Now, there are 4 different possible permutations of arrows around a variable. One of them is this one that we've just seen. Another one is that the arrows can be pointing away from it. A third one is that the arrows can be pointing in this direction. And a fourth one is that the arrows can be pointing into the measured variable. So let's look at each of these individual and learn about how a node which has each of these structures can be open or blocked. So if we look at this chart, we can see the principles about opening or blocking a particular node on a backdoor path. And in most situations, if you condition on a variable in the backdoor path, it's going to block that path. The only situation in which that won't work is this last one down here, which is when you have an arrow pointing into the node on each side of it on the pathway that you're looking at. And what happens is if you actually condition on that particular variable, you're actually going to open the pathway. And if you do nothing, then that pathway is going to be blocked. So if in your backdoor pathway you have this kind of situation, for example, let's change this. Let's say that COPD was a cause of smoking, and the tendency to use stimulants was also a cause of smoking. This backdoor path would actually be blocked without conditioning on smoking, because you have this structure where the arrow is pointing into smoking on both sides of the backdoor path. And as we saw over here, when you have that kind of situation, that node is actually blocked. Now, the interesting thing to note here is that if we, in that kind of situation, were to condition on smoking, we would actually open up this node. And since there are no other blocks like this where the arrow is pointing into the variable, for example, here, if the variable was pointing, or if the arrow was pointing into the variable on both sides, this one would also block the path, but it's not that way. So this path is actually now open. So in this situation, if the arrows were going in these directions, conditioning on smoking would actually open this backdoor path and would cause confounding in the association between coffee and COPD. So this is the general principle. Now, this kind of node where you have arrows going into the variable from both sides has a special name. This is called a collider. And basically it's because the arrows are colliding with the variable. So if you have a collider in your backdoor path, that backdoor path is already blocked at that node. And actually, if you condition on that node, then you're actually going to open up that path, or at least you're going to open up that node. And if there are no other blocks along that path, then the entire path will be open, and you'll have confounding between your exposure and your disease variable. In broad strokes, this is the principles of using a DAG to decide which variables you want to control, on which variables you want to condition to control for confounding between your exposure and your disease variable. Now, we will see more complex examples of this in class through your projects, and also I will be doing an example of my project, and the actual practice of using DAGs to do this kind of thinking about which variables to control will become clear as you see more examples. But at this point, you have all of the general principles. So the things to remember here are, one, in a DAG, missing arrows are the strong causal assertions. So if you're unsure about whether or not there's a causal association between two variables, you think there might be, but you're not quite sure, you should put an arrow there. This is especially true in chains of variables, or when you have multiple paths between two variables. When you have that kind of situation, you should really check to see if there should be any additional arrows between the variables to represent other potential causal pathways besides those ones that you have described. Now, conditioning on a common descendant will induce confounding between the two ancestors. That's something that we learned. We also learned that to use the DAG to think about confounding, what you want to do is you want to block all of the backdoor paths in order to control confounding. And we learned something about a collider. A collider is blocked naturally. If you condition on a collider, it becomes an open node. But other than colliders, conditioning on a variable blocks that node. And you want to remember, you don't want to block any nodes on the causal pathway between exposure and disease. And to see the causal pathway, you have to pay attention to the arrow's directions.